This is Mr. Hausman. We're going to be looking today at an application of centripetal force, which you've already watched an introduction video. I offered two, one made by Professor Dave, a famous YouTube physics channel, and then another one that's from a lesser known channel, but seems to explain the centripetal force really clearly. So I'm going to do a shorter version of that and really focus on how to connect the centripetal force to the QVB sine theta, or the magnetic force. Okay, so we're starting on page 6, if you're able to follow along or kind of follow the model. So in the previous video, you've already found out about how things moving in circles have this tendency to maintain their speed, but they're constantly changing their velocity. Because as they move around in a curved path or a circular path, their velocity is changing its direction. And I've only drawn 4 points on the circle here, but we refer to that as the tangent velocity. There's other kinds of velocities that can be described for circular motion, but we're going to focus on what is the tangent velocity. And as it turns out, it's a pretty easy thing to figure out because you know that velocity is equal to distance or displacement over time. And what is the distance around a circle? Well, it's 2 pi r. Now, why is the t over here capitalized? That's going to be something we use more of in the future. And t there stands for period. It's the time for one full circle. And therefore, the distance around the full circle divided by the time for the full circle, that ratio becomes your tangent velocity. So it's a little bit different than figuring out velocity in a straight line, but not that bad. Now, I am not going to spend the time right now deriving the acceleration formula, but because the velocity is changing, and depending on how tight that circle is, the speed at which you change that is a function of the velocity squared divided by r. I'll try to find another video or make one for people who are really curious, but that acceleration is unique to centripetal or center-seeking forces and accelerations. Notice in this picture, right, the A and the F are always pointed toward the center. At this point, the A would be pointed toward the center and the F would be pointed to the center. It seems to change its direction, but really it's uniform. The speed is uniform, and the force and the acceleration are always perpendicular to that velocity, no matter where you are in the circle. Okay, so when you take Newton's second law, which is not new to us at all, it applies to things moving up, down, left, right, even on diagonals. But essentially, when you take m times this A, you get a centripetal force formula. F equals m times v squared over r. Now, the one thing that the video doesn't explain well is that the centripetal force is not a real force. That is to say, it's really an adjective. It's an adjective that describes another real force that may exist in the world. So in my period 1 lesson today, we talked about how Lauren has a Jeep. And Lauren's Jeep, from a top view, right, has 4 wheels, and she's driving around a curve. Well, in order to get her car over here, or even to over here, right, she obviously turns the wheel or holds the wheel at an angle. And the wheels just seem to go around the curve. But why? Well, the fact is she's going around a curve. A curve is, in a sense, a fragment of a circle, a quarter of a circle in this case. And when she does that, her wheels, they may not be screeching. I hope they're not. But the wheels are experiencing a friction force, and it's actually a form of static friction. So let me be more specific. F static. And it's pointed toward the middle. Now, other things, such as maybe a lasso or a foxtail. It's a toy that I haven't seen around in a while, but it's about the size of a tennis ball, and it has a long nylon tail on it, and it's really fun to swing in the air and then try to send it to a friend. It might also be great as a dog toy. I'm pretty sure I've tried something like that with my dog. But the point is that there's other forces. It can be the static friction force, or maybe it's a tension force, because there's a tension between the swinging ball that you're swinging over your head and the and what you're holding in your hand, and that's the nylon string or the nylon tail. So here's a couple of the most common forces that can be actually acting as a centripetal force. So these are real forces, and they can play the role of a centripetal force. That's another thing I've developed over time, is to think of this as this is a role, and you have to find a character to play that, or a force to play that. So let's go to the first application. A proton is shot with a velocity perpendicular to a magnetic field. So I'm picturing a very large magnetic field, and here comes the charge. It's a proton. It's coming in perpendicular, and the magnetic field, whether it's uniform up or uniform down, it's a large room or a large plate where the magnetic field is known, right? We've got a B field here, we've got a velocity here. And it says find the radius of curvature, because the moment this positive charge experiences a friction force, so, sorry, I misspoke, not a friction force, a centripetal force, you have to remember that with the right-hand rule, with the magnetic force, the velocity and the force are always perpendicular. Oh, that's just like centripetal forces. So because the force is perpendicular, in this case, if the charge is up, it's going to curve to the right, and it's going to start circling, right? Its velocity is going to start changing, but its speed is going to be uniform, and it's going to go around in a circle. So what you do is you take two formulas that you have been introduced to, and because the forces, right, the magnetic force is causing the circular motion, you set them equal to each other. The centripetal force is being caused by a magnetic force. Well, that doesn't help you solve it, but as you know, we often do this. We do substitution. We can set two expressions equal to each other. QVB sine theta. And you're going to quickly recognize that one of the velocities on the left drops out. And from there, it's just a matter of rearranging. I prefer to do R is equal to, R over 1 is equal to mv over qb sine theta. That's your discretion how you rearrange that. The only thing that you might say is, wait a minute, I don't know the mass of a proton. That is very much something you can look up. I did that earlier today, and did I leave it and write it down? I didn't, so we'll just do a real quick search. Mass of a proton, 1.67 times 10 to the negative 27th kilograms. So you're going to need to use that for your mass. You have your velocity. You should be able to recall or look up the Q, the amount of charge that a single proton has. The B field is given, and we already said they're perpendicular, so we should be looking at sine of a 90-degree angle. And that's kind of how you set a magnetic force equal to a centripetal force. The follow-up question, part 2, just simply implies, what if instead of coming 90 degrees into the magnetic field, what if it comes in at a 30-degree angle? And the math doesn't change, so you have to still start with the whole equation, but you can clearly tell that our sine of 90 degrees gets replaced with sine of 30 degrees. And that's going to become a smaller decimal on the bottom, and I'm going to let you figure out whether or not the radius is larger or smaller, or actually calculate it. So that's kind of a start to these kinds of problems. And I know I've basically set up page 7 for you, and I'd like you to finish it. Okay, here comes a brand new challenge. It is part of, or it comes from the study of, or the physics of, mass spectrometers. And I asked you to watch a video. You may not have gotten to it yet, It's actually a little bit longer. I'm going to try to keep this one short. But essentially what we have going on here is we have a device that can separate out different size atoms, different size proteins, different size molecules from each other. But the first step is you have to ionize the material, make it charged, and accelerate it. So right here, a sample has gone into an electric field. And the electric field is caused by two parallel plates. And this is negative, so it's going to go against the E field. And if you remember, some of our notes said that E fields can do work. They can change the energy of the system. But really what's happening is that the potential energy right here is being turned into kinetic energy as it leaves the E field. And we actually have a charge or a conservation of energy situation going on. I misspoke there. It's just a conservation of energy. The potential energy it has on one side is a factor in the other. Now, I hope you also remember from previous calculations that you know what voltage is. When you measure electric fields, you often describe them what is the potential difference or what is the voltage difference across those fields. Think of it like a battery. And voltage is equal to the amount of electrical potential energy per charge. So fundamentally, we know that the potential energy of the charge when it enters the E field gets turned into kinetic energy when it leaves the plate. Okay? And you know the formula for potential energy from an electrical standpoint. It's equal to V times Q by rearranging the equation above. And the kinetic energy formula is 1/2 mv squared. Now be very careful. This is a capital V for voltage. And the little v on the other side is velocity. We'd be using slightly different shape letters if we were doing this, but let's use large and small because that's things you can easily keep track of. Okay, so if the accelerating voltage is 100 volts, okay, I know where to use that, and the electron has a mass of 9.1 times 10 to the negative 31st kilograms, I know where to use that. How fast is it going? And you ask yourself, well, wait a minute, they didn't give us the Q. I have to admit, you should be knowing what the Q is for a fundamental charge of an electron. But I'm going to write it out. 1.6 times 10 to the negative 19th coulombs. So with that, you now have a new... It's not the same as circular motion. It just happens to be connected in that we have mixed applications of fields. In this case, an electric field, causing a change in the types of energy it has. We've got the electric field doing work on it and giving it some kinetic energy. So then it emerges into a magnetic field, right? That's actually pretty strong, 0.2 Teslas. So you're going to have a velocity from the answer to your previous problem, check. And now what are we talking about doing? Well, what we're talking about doing is trying to figure out the fact that it's going to curve. This electron, when it enters into this magnetic field that's at the top of the page represented by these X's, right? I'm doing the right-hand rule in kind of in space. The magnetic field is inward. It's going to curve in to the right and create a circle. And we want to know what that radius of curvature is, because that will determine where it ends up. And we'll find out a little more about mass spectrometers. So you're going to have a velocity now. You're going to set Fc equal to F magnetism. You're going to know that mv squared over r, brand new formula, only developed a little bit earlier in this lesson. This formula for centripetal force is set equal to the real force, qvb sine theta. These are velocities. Those are not voltages. So we're done using voltage in the previous step. Okay, we've got a formula here that has voltage, and that gets you a velocity. Now we know the mass, we know the velocity, we don't know the r, and so this is almost like a continuation of page 7 now. Okay, I'm going to let you tackle the bottom of page 8. as an application of all of the ideas that have been introduced so far. Okay, now finally, some people panic when they say, wait, Hausman, you dropped an AP Physics open response question in and you expected us to do this. This is the non-calculus based physics. It's still very challenging, but it's still one that we can do. So I'm going to leave this one wide open. It does have a whole bunch of parts, A, B, C, D, but we're trying to figure out some questions about magnitudes of the various some quantitative answers, but we're also looking for some of the qualitative answers, some of the directions, and you want to be able to justify or explain your answer. So you're going to write out your work. There's probably room to do it at the bottom, maybe on line paper if you prefer. But I hope that gives you a good start into assignment on page 7, 8, and 9. Thanks a lot, guys.